It's pretty late. The glow of the monitor is probably the only light in your room right now.
Yeah, just that blue light.
Right. Exactly.
Yeah.
You got your IDE open, maybe a half-empty cup of coffee sitting next to your keyboard, and you were just, deep in the zone.
Oh, yeah. The coder's natural habitat.
Completely.
Yeah.
And as a software engineer, you live in this world of strict rules, right?
Yeah.
You define the types, you write the logic, you build the CI/CD pipeline. And in that world, there is one universal, undisputed enemy.
Bloat.
Bloat. Exactly.
Oh, I mean, the entire discipline of traditional software engineering is practically a war against bloat. We minimize dependencies, we refactor for O of n complexity. We basically try to strip everything down to its most elegant, lightweight form.
Yeah, because if an application is massive, it usually means something has gone terribly wrong somewhere in the architecture, right?
Right. It means technical debt or sluggish performance.
Yeah, exactly. But tonight we are taking a deep dive into some fascinating notes from the LLM Mastery series, and we are looking at a space where everything you know about optimizing for smallness gets flipped completely upside down.
It really is a total paradigm shift for a traditional developer. Because, in the realm of artificial intelligence and specifically large language models, bigger isn't a symptom of poor architecture.
No, not at all.
Bigger is actually the fundamental engine of capability.
Which is wild to think about. So our mission for this deep dive is to basically look under the hood of that AI scaling. We want to take these massive abstract concepts from the source material and, well, translate them into a framework that actually makes sense for those of us who spend our days writing traditional deterministic code.
Yeah, I love that.
Right. So we're going to answer, what exactly makes a large language model large? And mechanically, why does that size matter so much?
It's such a great late-night topic because it completely challenges your basic assumptions about how software works. When the industry says an LLM is, large, they aren't talking about a massive compiled binary sitting on your hard drive.
Right. It's not like a huge executable file.
Exactly. They are talking about scaling up 3 very specific interlocking resources.
Okay, let's unpack this.
Oh.
Because before we can even get into the heavy mathematics of scaling or the really wild phenomena that happen at the cutting edge, we need a baseline.
Yeah, a mental model.
Right. And the source material offers this really useful analogy to start with. It asks us to think of an LLM not as a traditional software program, but as a student.
I really like this analogy.
It's great, right? And that student's overall ability depends on 3 distinct variables.
Yeah.
So let's map those to the actual technology.
Okay, so the first variable is the student's sheer brain capacity, like how much room is up there. And in the LLM architecture, we call these parameters.
Now, hold on, because in an IDE, a parameter is just an argument you pass to a function, like string name, right?
Yeah.
Right.
But in a neural network, it means something entirely different.
It totally does. Think of a parameter here as a digital synapse. Technically, they are weights and biases. So floating point numbers in these massive, massive matrices.
Just huge grids of numbers.
Exactly. So when we say a model has 70 billion parameters, we mean there are 70 billion individual adjustable values that dictate how signals pass through the layers of the neural network.
Oh, wow. So that is the raw capacity for the system to hold complex representations of knowledge.
Exactly, the brain size.
Okay, so the second variable is the volume of material the student actually studies. This is the data. But again, to translate this for the engineer listening, we aren't just talking about, dumping raw text files into a folder.
No. The data represents petabytes of human knowledge. We're talking articles, books, code repositories, all of it stripped down, cleaned, and converted into tokens.
Oh,
Yeah, a token is basically a mathematical representation of a word, or even just a fraction of a word. So when we talk about the study material, we are talking about data sets consisting of trillions of these tokens.
Trillions. Okay, so we have the brain capacity, which are the parameters. We have the reading material, the tokenized data. The third variable in the notes is the total study time invested.
Which, honestly, is often the harshest bottleneck. In AI terms, this is compute.
And this isn't just like letting a Python script run on a server overnight, is it?
Oh, I wish. No, this is thousands of specialized GPUs, like the H100s, just running parallel matrix multiplications for months on end.
Whoops, wow.
Yeah, it's measured in FLOPs, floating point operations per second. So parameters, data, and compute. Those are the 3 dials you can turn.
See, this is where my mental model as a traditional developer hits a wall.
How so?
Well, if I am building a standard web app, right, and I hook it up to a massive PostgreSQL database with 100 terabytes of data, my application doesn't magically become smarter.
Right, it just has more stuff to search through.
Exactly. A huge database just means I have a lot of records to query. The application logic is completely static. It doesn't learn. So why does throwing data and compute at parameters create intelligence?
That's the core difference, because in your web app, the logic and the data are firewalled from each other.
Right. Yeah, they're separate.
The logic is a static set of instructions manipulating the data, but in a neural network, the training process actually blends them together.
Blends them.
Yeah, through a process called gradient descent. Basically, the model attempts to predict the next word in a sequence. When it gets it wrong, the system calculates the error, which is called the loss, and works backward to slightly adjust those billions of parameters.
Wait, so the parameters are actively reshaping themselves to internalize the statistical relationships within the data.
Exactly, over trillions of iterations. The parameters aren't just retrieving data, they are digesting the fundamental patterns of logic, syntax, and facts embedded in that data.
That's incredible.
Yeah, the most intuitive reason that larger models are more capable really comes down to what the sources call knowledge capacity. A bigger matrix of parameters can capture far more subtle and complex nuances in the training data than a smaller one.
Right. But a massive brain is useless if it hasn't read enough books.
Exactly.
And processing trillions of tokens through billions of parameters is physically impossible without a massive cluster of GPUs providing the compute. So you really need all three legs of the stool to scale together.
That is the foundational key to grasping modern AI architecture. It is not about writing a clever 1,000-line algorithm that suddenly achieves human-level reasoning.
Right. No goals in algorithm.
No, it is about architecting the infrastructure to orchestrate scale across parameters, data, and compute simultaneously.
Which brings us to the $50 million question. Literally.
Literally, yeah.
Because if you are an AI researcher sitting at a terminal about to spin up a training run that will cost your company tens of millions of dollars in compute time, how do you know the right ratio?
You definitely can't guess.
Right, you can't just blindly throw thousands of GPUs at a wall and hope a smart model comes out the other end.
You'd bankrupt your lab in a week doing that. And that brings us to what the industry calls scaling laws. The sources frame these as the rules of the game.
Okay, I have to push back a little on the word laws.
Oh.
Yeah, I mean, in physics, gravity is a law. In software, we have trends and best practices. But laws implies a level of mathematical certainty that seems, I don't know, overly confident for something as experimental as AI.
That's a really fair critique, and empirical regularities might be a more accurate term. But the reason they are treated like laws is because of how shockingly predictable the math actually is.
Predictable how?
Well, researchers discovered that if you plot a model's performance specifically, how well it minimizes its error rate on a log-log graph against the amount of compute, the parameter count, or the dataset size, it forms a perfectly straight line.
A straight line, like a power law relationship.
Exactly that. And the power of that straight line is extrapolation.
Oh, I see.
Yeah, by training a few small, cheap models, say a 10 million parameter model, then a 50 million parameter model, you can map that line. Then you can look at the graph and predict with startling accuracy what the error rate will be if you scale up to a 100 billion parameter model.
Before you spend a single dollar on the compute to build it.
Precisely.
So you basically have a blueprint. You know the exact return on investment for adding more servers or scraping more data. But wait,
Yeah.
if they have these log graphs, if performance is that mathematically predictable, does that mean the AI industry has always had this perfect mapping figured out? Like, we've just been following the same set recipe since the beginning.
You would definitely assume that, especially coming from a field that values deterministic logic. But the reality of language model development has been much more turbulent.
Really?
Yeah, the answer is no. For a significant period, the conventional wisdom guiding the creation of the world's largest models was fundamentally flawed.
See, this is the part of the deep dive that I just find fascinating. You were telling me that in a field moving at light speed, fueled by billions of venture capital dollars, the foundational math for how to balance the student's brain, study material, and study time was actually wrong.
It was significantly skewed. The earlier scaling laws, which are often associated with a highly influential 2020 paper from OpenAI, sometimes called the Kaplan scaling laws, they led the industry to a very specific conclusion.
What was it?
Well, those early charts suggested that as you increase your compute budget, the most efficient way to get a smarter model is to pour almost all of that extra compute into making the parameter count bigger, while keeping the amount of training data relatively flat.
So the industry philosophy was basically just build an absolutely massive brain.
Yeah. The assumption was that parameter count was the primary driver of capability. So labs raced to build models with 175 billion parameters, 300 billion, even half a trillion parameters.
Wow.
But they were training these gargantuan models on roughly the same size data sets, maybe just 300 billion tokens of text.
Okay, translating that back to our student analogy. They built a student with a supercomputer for a brain, but they locked them in a room with only a couple of encyclopedias to read.
That is exactly what happened, and that inefficiency wasn't fully exposed until a major course correction. Our sources highlight a landmark event in 2022.
The chinchilla paper.
Yes, published by a team of researchers at DeepMind, led by Jordan Hoffman. The source notes state quite explicitly that this single paper changed how the field thinks about scaling.
Just think about the mechanics of that for a second.
Yeah.
Imagine if a white paper dropped tomorrow that completely rewrote the core principles of relational database architecture.
It would be chaos.
Right. Proving that the way every major tech company has structured their queries for the last 5 years was fundamentally wasting resources. That is the level of paradigm shift we are talking about here.
Totally.
So what did DeepMind actually do to prove the old laws wrong?
They systematically tested the assumptions by varying both the model size and the data size simultaneously across hundreds of training runs. And what they discovered was that previous researchers had miscalculated the learning rate decay, which is basically how the model absorbs information over extended training periods. The chinchilla paper proved mathematically that to optimally train a model, parameters and data must be scaled in equal proportions.
Meaning if you double the size of the digital brain, you don't just keep the reading material the same. You have to double the amount of reading material too.
Exactly. The ratio they proposed is roughly 20 tokens of data for every one parameter.
20 to 1.
20 to 1.
Yeah.
Under the old laws, a 70 billion parameter model might be trained on a few 100 billion tokens. But DeepMind built a 70 billion parameter model, which they named Chinchilla, and they trained it on 1.4 trillion tokens.
So a significantly smaller brain, but it was forced to read a massively larger library.
And the result was staggering. The smaller Chinchilla model completely outperformed rival models that were 3 to 4 times its size.
Yep.
Yeah. It proved that the entire industry had been severely undertraining their massive models. They were wasting millions of dollars in compute on parameters that didn't have enough data to reach their full potential.
The chinchilla scaling laws course-corrected the entire tech world. Suddenly, every major AI lab had a new, optimized formula for how to balance compute, data, and parameters. But, this raises a huge red flag to me as an engineer.
What's that?
If the golden rule is now a 20 to 1 ratio of tokens to parameters, we're going to hit a wall, aren't we?
Ah, yes. You are hitting on one of the most pressing anxieties in AI research right now, the data wall.
Because parameter counts are theoretically infinite, right? So long as you can keep buying servers. But high-quality human data isn't. If we build a 1 trillion parameter model, the chinchilla ratio says we need 20 trillion tokens of data. Have humans even written 20 trillion tokens of high-quality text on the internet?
Probably not. We are rapidly approaching the limit of scraping high-quality, unique human text from the web. Wikipedia, Reddit, digitized books, academic papers, it's a finite pool.
So what do they do?
Well, researchers are exploring ways around this, like having models generate synthetic data to train future models, or turning to massive pools of video and audio data. But the Chinchilla paper permanently altered the landscape by proving that data starvation is just as detrimental as compute starvation.
Okay, so we have the components of scale, the parameters, the tokenized data, the GPU compute time, we have the log-log graphs that map the underlying physics, and we have the chinchilla paper that optimized those laws, telling us to feed these models way more data than we originally thought.
Right, the whole foundation.
But now we have to talk about what actually happens when you execute that optimized training run.
The output of the equation.
Right, because if we follow the chinchilla laws, we spend the $100 million and we scale a model up to an astronomical size, we expect it to just be better, right? Faster at generating text, fewer grammatical errors.
So that's the logical assumption.
But something else happens that completely shatters the mental model of a traditional software engineer. We move from the strict math of scaling into territory that honestly sounds like science fiction. In the notes, they call it emergence.
Emergence fundamentally challenges how we think about software capabilities. The sources defined emergent abilities as capabilities that appear to arise suddenly as models get larger, which are completely absent at smaller scales.
See, in our day-to-day jobs, Deterministic software does exactly what you instruct it to do and absolutely nothing more. If I don't import a library to parse JSON, my application will never parse JSON.
Never.
If I don't write the logic for an export to PDF function, no amount of extra RAM or CPU speed is going to make the app suddenly figure out how to generate a PDF.
Exactly. A traditional code base scales linearly in performance, not qualitatively in features.
But in the world of language models, you follow the scaling laws. You increase the parameters, you feed it trillions of tokens, you run the compute. You never explicitly program the model to write Python code. You never explicitly program it to solve logic puzzles. But suddenly, a brand new capability just emerges.
It's a profound shift in software engineering. I think the best analogy to grasp this actually comes from physics.
Okay, let's hear it.
Consider a single molecule of H2O.
Right,
A single molecule doesn't possess the property of wetness.
right. It's just atoms.
Exactly. Wetness isn't a characteristic of the molecule itself. It is an emergent property that only exists when you have billions of water molecules interacting together under specific conditions.
That's a brilliant way to frame it. Wetness is a byproduct of scale and complex interaction.
Yeah. In neural networks, it is a similar phenomenon. At a smaller scale, say, a few million parameters, the model might just be good at statistical parroting. It learns basic grammar. It learns that the word apple often follows the word red.
Just a really sophisticated autocomplete.
But as you scale it up, as the parameters and data cross a massive computational threshold, the model is forced to minimize its error rate on increasingly complex texts. To accurately predict the next word in a complex physics textbook or a dense block of C++ code, simple statistical parroting is no longer enough.
So what does it do?
The network is forced to develop internal representations of the underlying logic.
It has to build an internal world model to figure out what word comes next.
Precisely. And in doing so, suddenly the model can translate between languages it was never explicitly taught.
Yeah, researchers didn't go into the matrix and write a pass medical exam module.
They couldn't even if they wanted to. The billions of weights are a black box. The researchers merely scaled the underlying system according to the chinchilla laws. The capability emerged from the sheer complexity of the internalized patterns.
That's incredible.
The massive digital brain digested enough data that it began to infer abstract rules and relationships without direct instruction.
It is mind-bending. It means that as a developer moving into this space, you aren't really a builder of rigid specific tools anymore. You are cultivating an environment.
Cultivating, I like that.
Yeah, you're balancing the compute, curating the tokenized data, setting the parameter architecture, initiating the gradient descent, and then just observing the loss curve to see what the system becomes capable of doing.
It's a transition from engineering predictable structures to gardening highly complex probabilistic systems. And emergence is the ultimate proof that the bloat we fiercely avoid in traditional software is the actual lifeblood of AI capability.
Right.
Expanding the footprint isn't a symptom of poor optimization. Expanding the footprint is the catalyst for intelligence.
So to synthesize this late-night deep dive, if you want to understand what makes a language model large, you have to look past the file size on disk. It is a calculated mathematical balance.
Yep.
It is the parameters acting as the digital synapses. It is the trillions of data tokens acting as the study material.
Yeah.
And it is the massive GPU compute driving the learning process.
And we now know that balance is strictly governed by scaling laws, plotted on log graphs that act as the predictable physics of the field. Laws that DeepMind's chinchilla paper recently redefined, proving that we must feed our massive digital brains vastly more data at a 20-to-1 ratio to unlock their true potential.
And when you nail that math and you scale the infrastructure up to astronomical levels, you unlock emergence. The system transcends simple next-word prediction and learns to execute entirely new qualitative tasks that break the bounds of deterministic programming.
It really is wild.
Grasping these levers is the fundamental bridge for any software engineer looking to step into the dynamic world of AI.
It forces you to rethink the boundaries of what software can do when you stop trying to control every single variable.
But it also leaves us with a lingering, almost unsettling question to ponder as we wrap up tonight. We know that scaling laws dictate that simply increasing the compute, the parameters, and the data unlocks these sudden, unpredictable, emergent capabilities.
Right.
We have mathematically proven that bigger yields smarter. But is there a ceiling to this?
That is the ultimate unknown hovering over the entire industry right now. Do these log-log graphs eventually plateau?
Right. Or will the next massive order of magnitude in scale, like the next time we spin up 100,000 GPUs and feed a trillion parameter model, every piece of data ever generated, will it unlock emergent capabilities that we haven't even thought to test for yet?
It is definitely something to think about the next time you are compiling a perfectly predictable, deterministic block of code.
Keep that in mind as you finish your coffee and get back to your IDE. Until next time.